So looking at this function, we can see that it appears to be concave upwards until a, and then concave downwards after that, just through intuitive knowledge of concavity, but that's not really a mathematical definition, so let's look for one. We can see that before a, when we were saying it's concave upwards, the slope, visualized here with the derivative, is increasing, right? So up here on the function, we have the slope is negative, and then it's less negative, and then it's 0, then it's positive, and then it's more positive. And that makes that U shape that we associate with concave upwards. And then beyond that, when the slope is decreasing, it's concave downwards, because the slope is going from positive to less positive to 0, and then negative, more negative. And then in the middle, where it's neither concave upwards nor concave downwards, we have this extrema point. At this point, the slope is non-zero, right? We can see that it's clearly increasing. However, for any x values less than x equals a, the slope is increasing, right? It's concave upward. And for any x values greater than x equals a, the slope is decreasing, and it's concave downward. This point, where it switches from being concave upward to concave downward, and where the slope switches from increasing to decreasing, or vice versa, that is called an inflection point. There's a way to check for these inflection points too. Since we know the slope, in this case it's switching from increasing to decreasing, has an extrema, we know that the second derivative at that point has to be equal to 0. So if you're trying to find the inflection point, just given like a function, you find the second derivative of that function, and then you solve for its zeros. And where that function equals 0, you have an inflection point. So in a situation like this, where the function is switching from concave upward to concave downward, the slope is switching from increasing to decreasing, that means that the second derivative is switching from positive to negative. In fact, when the second derivative is positive, the base function will always be concave up because the slope is increasing. And when the second derivative is negative, the base function will always be concave down. As an example, say you're trying to find the inflection points of f of x is equal to negative 1/3 x cubed plus 3x. So you need to find the second derivative, right? Because at the zeros of the second derivative, you know you're going to have an inflection point. So let's find the first derivative, which by an application of the product rule is going to be negative x squared plus 3. And then, again, for f prime prime x, we're just going to do another application of the product rule. We get negative 2x. And this is our second derivative. So the zeros of this second derivative, those are going to be our inflection points. And negative 2x is equal to 0 when x equals 0. So for this function, our inflection point is that x is equal to 0. Thank you.